Okay, so I was saying yesterday, almost every planes problem I've ever done involves some level of critical thinking. So whether it's figuring out your normal vector or something else, usually the normal vector, the givens are always different and the expectations are always the same. In the end, you're supposed to come up with a scalar equation of a plane. So let's just write down what our main strategy is. Our main strategy is to dot the normal vector with x, y, z, and dot the normal vector with a position vector for a point in the plane. So the left side is going to give you variable stuff. For example, if this is like, 3, 4, 5. I'm sorry, if the normal vector is like 3, 4, 5, then it's going to give you, like 3x plus 4y plus, 5z. That will be your left side. It's always going to look like that, And then the right side will be all numeric, because this will be like 3, 4, 5, and this will be, some other vector maybe, like, -2, 6, 7. And then when you dot these, you get -6 plus 24, and, plus whatever, 35. So what I'm saying is you always end up with the same kind of result, something that looks like 3x plus 4y plus 5z equals 53. Okay? So the objective is always the same, but the getting there can be hard. So like on this first problem, I actually said, hey, look, I want to find the equation of a plane that's normal to a vector. Well, that's the same thing as saying find the equation of a plane with a normal vector, 3, -1, 1. So without trying to draw anything to scale, imagine your plane. This is the plane you seek to find. And there's a vector that's already normal. You already know that. It's the vector 3, -1, 1. And then it mentions the origin. Well, if the plane passes through the origin, then you can expect that 0, 0, 0 is on the plane. And you can use that as your x naught, y naught, z naught, see? So the theory is very simple. The idea is, look, if you happen to know the direction of a particular tree standing up on a surface, and you know one point on the surface, you can predict where the ground is. Or, if you happen to be looking for a specific surface and you know the direction it's perpendicular to, then you kind of know the direction it's parallel to, because there's 90 degrees difference. And then if you can find one point, that will nail down the actual vector. So some people always want to know, like, hey, is the red vector actually touching the blue point or not? That is a silly question. Sorry, but it is. The red vector, you should be allowed to place it anywhere you want. So yeah, you can place it so its tail is right on the blue point, or put it anywhere else in space. Vectors are fully translatable in space. You can put them anywhere you want. So envision the red vector wherever you like, just keep it perpendicular to the plane. Okay, so on this first one, it's really simple. You're just going to basically go, hey, look, we're going to use the normal vector. This is n. We're going to dot that with x, y, z. Then we're going to take the normal vector, and we're going to dot that with 0, 0, 0. And so the answer is literally 3x minus y plus z equals 0. And that's the answer. Okay? Next is find the scalar of a plane that contains these 3 points. This is a little more complicated, but if you call the point P 2, 1, 4, and you call the point Q -1, 3, 5, right? And you call the point R 6, -4, 8, know that these 3 points, P, Q, and R, are all already on the surface of the plane, right? So since your goal is always the same, get your normal vector, dot it with x, y, z, get your normal vector, dot it with x naught, y naught, z naught, you have to have a normal vector. Right now, you could construct, if you wanted, 3 different vectors in the plane. You could find vector PR, vector RQ, vector PQ, there's actually 6 of them, vector QP, vector RP. There's 6 possible vectors you could jot down right now. But none of them are normal to the plane, unfortunately. That's bad news. So what you're going to do is basically create 2 vectors, maybe P, Q, and PR, or something. Then you'll do a cross product, and what that will do is it will create a 3rd vector sticking straight out of the plane, perpendicular to both P, Q, and PR. In other words, you'll create a normal vector. So that's actually going to be our goal. We're going to find P and Q, the vector PQ. So to do that, you just basically do Q minus P. So you get negative 3, 2, 1. Sorry about that. That just kind of popped up. Give me a second. I've got to find my document here. This one. Yeah, sorry. That's vector PQ. I just did head minus tail for Q and P. And then you need vector PR, maybe. For that, you do R minus Q, or R minus P. So basically 4, negative 5, 4. And then if you do a cross product, you can get your normal vector. So a little bit awkward to do a cross product. You just take these. You could do it in any order. So hopefully you know how to do this. If not, just bear with me. You're going to do 8 minus negative 5. 8 minus negative 5 is, well, 8 plus 5, 13. Right? And then you have these outer ones. So you do 12 minus 4, which is 8. But you change the sign on that one. So it's actually negative 8. Negative 12 minus 4 is negative 16. Sorry. Negative 12 minus 4, negative 16. We change the sign on that. It's positive 16. Don't forget the mandatory sign change there. And then lastly, use the other 4 in this corner here. So it's 15 minus 8, which is 7. And don't change the sign. So how many of you got 13, 16, and 7 as a normal vector? So kind of a lot of work, but that's what we needed. I'm going to erase all of this garbage. 13, 16, 7 is a good normal vector. 13, 16, 7. Or you can use the opposite of that. Negative 13, negative 16, negative 7, which is fine. That'll work too. So we're going to go 13x plus 16y plus 7z is equal to. And then for your right side, you're going to use 13, 16, 7. And you're not going to use vector PR or QR or any of that. You're just going to use one of the original points on the plane. So like 2, 1, 4, for example. And turn it into a vector. So it's the vector 2, 1, 4. And you're doing a dot product. So this gives you 26 plus 16 plus 28, which comes out to 70. And this is the answer. Okay, so that's the equation of our plane. And then I asked you to find the equations of the traces of the plane. And some people get all worried about this, but don't stress out about that. I'm just basically saying, look, this plane that we just created, or just found the equation of, most likely hits the xy plane, and the yz plane, and the xz plane. So let me just kind of demonstrate that. If you just randomly draw a plane in space, like this, just randomly, you're probably going to end up getting contact with these more familiar planes, xy plane, which I've been calling the desk, the yz plane, which I've been calling, or it's kind of like straight up and down on the desk, and the xz plane. So I just want the sides of this triangle. They're all lines. It's very simple. If you want to find the xy trace, you basically cover up your z. You just make your z 0, and you get 13x plus 16y equals 70. That's your xy trace. So 13x plus 16y equals 0. If you want to find your yz trace, what variable do you suppose you would make 0? Make your x 0, right. So now it reads 16y plus 7z equals 70. Sorry, a little hard to read over here. That's a z. And if you want to find your xz trace, make your y 0. So if you want to find the xz trace, make your y 0. So it's 13x plus 7z equals 70. And these are equations of lines, and they are the trace lines. They're kind of like the lines of contact with the 3 initial planes we started with. Okay, let's go to number 3. Find the equation of a plane tangent to, that's a typo. It should say, find the equation of the plane tangent to the cylinder with a spherical coordinate equation rho equals 10 sine phi. Okay, so this one's just a little bit tougher and a little bit hard to visualize. So, okay, so I'm going to scribble on this document, and basically I'm going to draw a really big picture. So, okay, so this is X, Y, Z, and then there's this cylinder. They called it rho equals 10 over sine phi. But honestly, rho equals 10 over sine phi. If you cross multiply it, you just get rho sine phi equals 10. Or if you think in terms of cylindrical coordinates, that's just r equals 10. In the cylindrical world, rho sine phi is just r, is all it is. So I just converted from spherical back to cylindrical. So what are you going to do with this thing? Well, you're going to be convinced that it's a radius 10 cylinder. Okay? So let's go and draw that. So imagine a radius 10 cylinder. Okay, so something like this. If Sydney were here, she could draw a much better picture. Something like that. I don't know how important the picture is. It just depends on how comfortable you are with this. But I gave you a specific point on the cylinder, namely the point 6, 8, negative 3. Now, can somebody tell me why we know for certain that this point is right on the surface of the cylinder? How do we know it's on this surface, this lateral surface? Yeah, this is a Cartesian or rectangular, right? If you convert it to cylindrical, so that way everything's kind of in cylindrical, you would use these two to do 6 squared plus 8 squared square root, so that's just 10. The z, you would just steal that, negative 3. And if you want to calculate the angle, it's probably not real important, but inverse tan of 8/6, I think it's 53 degrees. What we're saying is this is the point on the radius 10 cylinder. It's a cylindrical coordinate, so the first value tells you the r value. So anyway, this is definitely on the cylinder. Now you kind of visualize that particular point a little better. I think I will actually draw that point. Okay, so I'm going to do all my drawing in green from now on. So if you basically go in the 53 degree direction, 10 spaces out, and then drop by 3, you'll find yourself down here on the surface of the cylinder, sort of in the back. And this is the point. Let's call it point P. Okay? Now, supposedly, there's this plane back there that's tangent to the cylinder. I think you can probably imagine that. I'm sure you can imagine a plane tangent back there. So what are the ingredients for getting the equation of a plane? What do you have to have? Minimum knowledge to create the scalar equation of the plane. What do you need? What are the two ingredients? A perpendicular vector, n, and a point vector, right? I have no problems with you just using 6, 8, negative 3 as a position vector for that point x naught, y naught, z naught. I do have an issue with you using 6, 8, negative 3 for your normal vector. I don't think that 6, 8, negative 3 is really, truly perpendicular to the plane. You know what I mean? 6, 8, negative 3, I haven't drawn it yet, but it's right here. I don't think that thing's perpendicular to the plane. The plane is standing straight up and down, you see. And that's kind of pointing downish. That make sense? Can anyone see a vector that I've actually already drawn that is perpendicular to the plane? this one right here, that thing is perpendicular to the plane. As it leaves the axis of the cylinder and it goes right through the surface of the cylinder, it does so in a nice right angle fashion. It exits the cylinder poking straight out. Right? And that is the vector 680. 680. It doesn't have a z component, but it lies in the same direction as 68, negative 3, you know. So basically, 68, negative 3 is down here. That's a great position vector. Horrible normal vector. It's not perpendicular, but this one here, 680, makes a good normal vector. Okay? So we're going to use 680. And like I said, that's the critical thinking part of it. Now you might argue, I don't want to use 680, I want to use something else. That's fine. We'll all agree on the same answer. That's the beautiful part. Let's say you wanted to call it 340. That works. Or 6080. That works. You can make it go backwards if you want. Negative 6, negative 80. It doesn't matter. You flip it around the other way, and I'll just stick it over against the plane. It'll still be perpendicular. And the answer now is just basically 6x plus 8y plus 0z equals, and then whatever 680 dotted with 68 negative 3 is. Looks like 36 plus 64 plus 0. So basically 100. So my final answer on this problem is 3x plus 4y equals 50. I actually reduced it all down. I'll write it at the top. 3x plus 4y equals 50. And then I asked you to find the X and Y-intercepts. After all, this green plane that I've drawn probably does hit the X and Y axes, doesn't it? It's just kind of angled, and I think it's going to tap right through the x-axis somewhere and through the y-axis somewhere. Okay, so just kind of going back to our document, I'll just put my answer on the document, find the two intercepts, and we'll be done with it. So my answer was 3x plus 4y equals 50. As for x-intercept, that would naturally just occur where x is equal to a number, but y and z are both 0. You know, so basically I'm going to force that. I'm going to make y and z both 0. I don't really see a z. So I just basically get 3x equals 50. X is 50 thirds. And if you want to find a y-intercept, I'll show that over here. That would just be a number, you know, x is 0, y is something, z is 0. So I'm going to make x and z both 0, just to see where it taps through the y-axis. So I just get 4y is 50, y is, you know, 50 halves, or 50 fourths, or 25 halves. That's all. You're not doing anything new here. You're just interpreting intercepts in the 3D realm. So graphically what that means is, since this is approximately, what, 16.7, and this is 12.5, if you go back to this picture, right here, where this green plane taps up against the x-axis is right about at x equals 16.7 or so, see? And where it hits the y-axis is more like 12.5. Y is 12.5 right there. So it's just these two big black points. That's all it is. Are you surprised that it doesn't hit the z-axis? Not if it's standing straight up and down. I'd be shocked if it hit the z-axis. It shouldn't. So what's the hardest part of this problem? Most people say that the hardest part is getting that normal vector. The rest is just mechanics, you know? But there is some critical thinking, and I can't help it, okay? And then our next problem is a sphere. Find the equation of a sphere. I'm sorry, find the equation of a plane. Tangent to a sphere. And I don't know if you thought about this, but this is really just rho squared equals 16. In other words, rho is 4. Don't put plus or minus. Rho is a distance. So what's the size of this ball? What's the radius? 4. Yeah, naturally. Okay. So let's go back to our blank document and we'll draw a radius 4 sphere. See if we can understand this better. So here we have I already know I'm going to mess this drawing up. Here you have a sphere. Okay. And there is a mention of the point 0, 0, 4, but we don't need it yet. It'll be kind of our last part of this problem. It has nothing to do with the first part of this problem. So first thing we're going to do is find the point root 2, root 3, root 11. That's a weird point. Be gracious to me, though. I was looking for a point that would be on the sphere. It took me a minute to think of one. But if you square these and add them up, it comes out to 16. So I was just trying to dream up something there. That's probably in what we call the first octant. There are no longer quadrants, folks. There's 4 quadrants. But now we have regions above the quadrants. So let me just teach quadrants or octants real quick. It's very simple. If this is your x-axis and this is your y-axis, this is called quadrant 1, and this is called quadrant 2, and this is quadrant 3 and 4. Naturally. That's just algebra 1. But now that we're in 3 space, we have basically 8 regions to study. We've got the region directly above quadrant 1. This region directly above quadrant 1 is often referred to as octant 1. And there are actually 8 octants altogether. There's the region above quadrant 2, and there's the region above quadrant 3, and the region above quadrant 4. And then there are 4 lower regions. So there are 8 total octants. And I honestly don't remember how they're numbered. If they go, just 1, 2, 3, 4 around counterclockwise again, and then the bottom ones are 5, 6, 7, 8. It doesn't matter what you call them. The point is, this particular point is an octant 1, right? It's positive, positive, positive octant. Okay. Okay, so that being said, our point's over here somewhere. Right on the ball. And imagine the green plane again, tangent to the sphere. All right, so here is a side view of everything. Here's the ball. Here's the random point P that I gave you. The green plane, you're looking at its edge. It's coming out at us, okay, like this. Watch my hand. Sticking out like this. Okay, I don't know how to record that. And then we seek to find its equation. Well, what are the 2 ingredients for finding a plane? What are they again? A normal vector and some point vector, right. Well, for the point vector, you can just use root 2, root 3, root 11. It literally is basically the vector from the center of your object, which fortunately for us is the origin, to any point on the sphere. Since this is the point P, we can just simply use the coordinates of the point as one of the points on the plane. Excellent. But something interesting also just happened. If you're looking for a normal vector, you don't have to search very hard to find one. Why? We need a normal vector. We need some vector that's perpendicular to the plane. We can just use this same vector, can't we? I mean, not only does this root 2, root 3, root 11 describe this black vector, that vector already is normal to the plane, you see? So we're going to use it again. We're going to use it as our n also. This is very, very, very rare. The only time this ever happens for all points is the sphere. Okay? So we got really lucky in the critical thinking part of this. A good sketch answered the question, this is both n and it is x naught, y naught, z naught. And some people insist, don't make your normal vector so long, for crying out loud. Make it a unit vector. It's like, who cares? not going to scale it down. I don't care at all. My results are going to be perfect. So now we go back to our equation, and we're going to do n dot xyz equals n dot x naught y naught z naught. The left side is just root 2x plus root 3y plus root 11 z. The right side is root 2, root 3, root 11, dotted with its own self. So if you're in physics, you know that when you dot a vector with itself, you just basically square its magnitude. But here, we'll just work it out. It's root 2 times root 2 plus root 3 times root 3 plus root 11 times root 11, 16. So here's the answer. Root 2x plus root 3y plus root 11z equals 16. How hard is this problem really? It's not hard. It's just a matter of really seeing it. You know? That's the hard part. And that's always going to be the way it is in 3D. Visualizing will be the hardest part. Really, there's no critical thinking in that problem either. It's a good sketch. Or maybe visualize it right off the bat. Okay. And now let's answer the last question. Find the symmetric equations of the line normal to the plane that passes through blah, blah. What is it talking about? Well, this is a lesson 2 problem where you find the equation of a line. What are the necessary ingredients for finding the equation of a line? This is a totally different lesson. Remember, it looks something like this. Vector plus t vector. Okay, initial vector point, we call this a position vector for initial point. And then the other one is a what? It's called ABC. Do you know what it is? It's any vector that's on the line. Any vector that's on the line itself. So I don't know how much sketching we need to do, but it'd be nice to kind of at least know what we're accomplishing here. Let's go back to our drawing. Our goal now is to find from this point 0, 0, 4, which is right at the top of the ball, actually. There are many, many lines that pass through this top of the ball. Infinite number of lines that pass through the top of the ball, right? But only one of them is normal to the plane, the green plane, not the ball, the green plane. So imagine the green sheet. You know, it goes on forever. Let's sketch it a little bigger, you know. It goes on and on and on. It's a big sheet, right? Infinitely big. I can imagine maybe that there's one line, exactly, that passes through the big green blob at the top, and it's perpendicular to this plane. That's the only line I can think of. And I want its equation. Well, the 2 ingredients I need for this big red line are one point, which I already have, 0, 0, 4, and a normal vector, which I can steal from the previous part of the problem, because although this vector is shifted up here, it's still a normal vector. And it doesn't even change names when you shift it. This is still the vector root 2, root 3, root 11. It's the same vector as before. Still points in the same direction as the radius, you know. Okay, so back to the drawing board, or the writing board. We're going to be using 0, 0, 4 as our point on the line. T is a variable, leave it there. And we're going to use root 2, root 3, root 11 again, because we believe that that vector is still perpendicular to the plane, right? And this is the answer. There are 3 forms for such an answer, remember, at least. And the ones we talked about were x equals 0 plus root 2t, y equals 0 plus root 3t, and z equals 4 plus root 11t. I just basically distributed, I'm treating this left side as a vector x, y, z. So I'm just distributing and creating 3 equations, right? And then the symmetric form is where you isolate t in each of them and set them all equal, right? This doesn't always work, but it works out well on this problem. If you isolate t in this first one, you get x over root 2. If you isolate t in the second one, you get y over root 3. And if you isolate t in this last one, you get z minus 4 over root 11. So your final answer for the symmetric equation of the line normal to the plane passing through 0, 0, 4 is basically x over root 2 equals y over root 3 equals z minus 4 over root 11. And now that you have an equation of line, you could talk about the line, you know. You could even construct another plane up further in space that's perpendicular, you know, to this line somewhere else. And the whole point of this is to get you to think about positions and lines in space and planes passing through those lines. And I think we've more than scratched the surface of that sphere, right? Can you imagine me writing a problem maybe where I give you the equation of the plane and ask you to write the equation of the sphere? I totally could have reversed this question. I could have given you the equation of the plane, and then from there you would have to figure out, oh, that's a radius 4 ball. And then from there you could write the equation rho equals 4. So this whole problem can be switched backwards. I could have given you the line first, and you could have created the plane. There's so many things I could do with this problem. So be flexible. And bring your worksheets. I'll let you use them during the quiz. Okay? But not notes. I won't let you use your notes. Only the worksheets that you've done. Yeah. Maybe, actually, I think I'll probably just have you use this worksheet only, because this has the most detailed sketching and stuff. So. Okay, we're actually done with points, lines, and planes. What took one day in geometry took, what, a whole week in Calc 3? And so, next topic is limits. I already gave you the notes.